Hey, welcome back. This is the exercises video for section 1.3, new functions for mold. We've got 5 problems here to work on, and I think they will be pretty short and pretty quick, so let's see. Jumping right into our first problem, this is number 5 from the textbook, and for this group of problems, it gives us a graph, and it asks us to apply a certain transformation and show what the new graph looks like. So this is the graph for m of t, and it asks us here to draw the graph for p of t that we obtain by subtracting 1 inside the function. So we have to remember our 4 transformations. Subtracting or adding a number inside causes a horizontal shift, and this is the one that feels a little bit backwards. Subtracting a number shifts to the right, adding shifts to the left. And the explanation for that in the lecture video was that, for example, if you're adding 5 inside, that means your new function pulls the values from your old function over from 5 to the right. So that's like taking the old one and moving it to the left. So here we are subtracting 1. So that means we want to shift m right by 1 to get p. So that's all we have to do. Let's graph this real quick. Oops. Now the leftmost point in the graph that they gave us was -3. So since we're moving to the right by 1, we only need a -2. That's our -1 and 0. And since they went up to 5, we have to go up to 6. For the heights, we're not doing any height change, so we need the same heights of 2 on top and -1 on the bottom. So now all we need to do is draw the graph that they have, shift it over by 1. So their graph started at -3, -1. That means ours will start at -2, -1. Then we follow the same behavior. It goes over by 1, and then up for a while, so we go over by 1. Now they go up to the point 1, 2. We're going to the right by 1, so we go to 2, 2. That means we're going up to here. Then they do this little kind of semicircle thing that goes over by a total of 2. So we do that as well, going from 2 to 4. The bottom of their semicircle was about at 1, and we're not changing the heights at all. So same kind of thing. And then lastly, they go down from 3, 2 to 5, 0. So that means we go from 4, 2 to 6, 0. Maybe an easier way to do this from the start would have been to go to their graph and label each one of these points, -3, -1, -2, -1, 1, 2, 4, 2, and 5, 0, and then shift those all to the right by 1 by just adding 1 to each of the x coordinates. Draw those dots on your new graph and then connect them. But either way, that's our answer. All we needed to do is figure out what this meant and then draw the graph. Hopping over to our second question. Now here, they define 2 functions, f and g, and they ask us to compute 5 different quantities. Each one of these will be pretty fast. So let's start with a. This is a composition of functions. This is f of g of 1. So what does this say? We go from inside to outside. It says, first, plug in 1 to g. That's like feeding 1 into the g box, and we'll get some output. Then whatever that output is, feed that into f. So we'll draw a little picture up here. That's like, first is g because it's inside, and then f. We feed in 1. And okay, if we feed in 1 to g, what's our output? Well, g of x is x plus 1. So if we feed in 1, we get 2. Then we take that output and we feed it into f. If you plug in 2 to f, what do you get? F of x is x squared. So we square 2 and we get 4. So let's write this as f of 2, which is 4. Part B is kind of the same thing, but in reverse. This is g of f of 1. So first we plug 1 into f, and we get 1 squared is 1. That output now gets plugged into g. So now we do g of 1. G of x is x plus 1, so you add 1 and you get 2. Now C and D are the same kind of idea. We're going to do the composition in both directions, but not with a plugged in number like 1. We're going to leave it with the indeterminate x, like we did in one of the examples in the lecture. So f of g of x. Well, that's like going through the g box first. You plug in x, and what you get back, g is the function that adds 1. So the output there is x plus 1. That x plus 1 then gets piped into the box for f. F takes whatever you give it and squares it. So the result is x plus 1. So let me write this in 2 steps. That's f of x plus 1, which is x plus 1 squared. Now, as a preview of something that we're going to need to remember how to do later, you should hopefully remember how to factor out, how to multiply out when you have a binomial like this squared. That's the FOIL, the first, outside, inside, last. So make sure that you remember how to get x squared plus 2x plus 1. Part D is the composition in the other direction. When you plug x into the f machine, it spits out x squared. So now you're feeding x squared into g. G takes whatever you give it and adds 1. So that's x squared plus 1. Lastly is something a little bit different. This is f of t times g of t. So this is just a times in the middle. Now you remember that a lot of times in math, multiplication is implicit. If we just write two things next to each other, that really means multiplication. Just like if we had written 2x, that really means 2 times x. So this is just whatever f of t is and whatever g of t is. Now, it's really tempting here to write the following thing, which is wrong, and Wiley Plus would not give you credit, and you might be confused at first. Why not? So here's the wrong answer. Well, first we look at f and get x squared. Then we look at g and get x plus 1. So we write x squared times x plus 1. And if you want to multiply that out, that's x cubed plus x squared. Now, hopefully you're taking my advice, and before you watch me do each problem, you're pausing and trying them on your own. That's a really, really strong advice that I'm giving you. I think it's really important. So if you did that, you either have this, in which case you made the same mistake that I did here, or you got the right answer. Now, if you weren't pausing, maybe pause for 1 second and think, why is this wrong? The reason it's wrong is that we're not plugging in x, we're plugging in t. So that means all of our x's have to become t's. So our correct answer is t squared times t plus 1, which you could expand as t cubed plus t squared. So that's the fix. Wiley Plus is normally pretty smart in the sense that if you simplify something in a slightly different way, it can know that it's equal to its version. But this is a different kind of thing. This is actually using the correct variable. So it will appropriately mark your problem wrong if you have the wrong variable, because it is genuinely wrong. So you have to always be checking your variables. Okay, that was our second problem. Moving on to our third. This is an example of asking if a function is even, odd, or neither. And we did 4 examples of this in the lecture, so this should be pretty quick. We remember that our test is to plug in negative x and see if what we get back is either the same thing we started with, then it's even, negative of what we started with, then it's odd, or if you don't get either of those, then it's neither even nor odd. So let's plug in negative x. We need parentheses to make sure the negative is grouped in with the x. That's negative x all to the 6th plus negative x cubed plus 1. And then we have to remember how the negative sign behaves under a 6th power. Well, 6 is even. So if you take 6 negative signs, they cancel out to a positive. This is negative x cubed, so that's an odd number. So that's 3 negative signs make a negative. So really, instead of a plus, I should put a minus x cubed, and then plus 1 stays the same. So is this the same as f of x? No, because this has a minus and this has a plus. So it's not even. Is this the same as if I, as negative f of x? No. That would mean each one of these terms had to be the negative of what I started with. And the x cubed is, but the other ones aren't. So this is not perfectly negative f of x. So it's not that. And that means it's not odd. So simply, it's neither. Okay, problem number 4. We're making quick work of these. Again, if you are, I recommend that you pause and you try this problem, and then when you get stuck, start watching the video again. This says use a graph of the function to decide whether or not it's invertible. And we had a test to decide if something was invertible. It was called the horizontal line test. If you can draw a horizontal line through the function that crosses it more than once, then it can't be invertible, because then when you flip it, then you get a vertical line with 2 points, and that's not a function. So the trick here is trying to realize how to graph this function. Now we want to be able to do it without a graphing calculator, without the internet, because this is a very simple type of function that we can do that with. These simple ones that are second powers, these are quadratics, and we should remember how to graph them. Now anything that's a quadratic, meaning its highest power is 2, we'll talk more about these in 1.6, but you probably remember most of it from pre-calc. They all either look like this or like this. And which one depends on whether this leading term is positive or negative. Here it's positive, so it's going to look like this one. The question is just where it crosses the x-axis. Now, I guess at this point we could stop and say, wait a minute. It doesn't matter where it crosses. If it looks like this, it's going to fail the horizontal line test. And that's true, actually. This function here, let me just draw a little axis for us. Imagine that I take this function, and maybe it's here, or here, or here. It doesn't matter where it is. No matter where this is, it's going to fail the horizontal line test. So I guess at this moment, we could just stop and say, no, not invertible. But let me remind you, just for the moment, how to figure out where this graph is, because that's a skill that might be useful in a later section. The key is to figure out, since it's a quadratic, figure out where it crosses the x-axis. That means where is it equal to 0? We're asking which x values, if I plug them in, give me 0. That's the same as saying, where am I going to cross this x-axis? And if I know where, say I cross here and here, then I know that my graph looks like that. I guess I still need to figure out where the bottom of that loop is, but most important is where it actually crosses. So the easiest way to figure out where a degree 2 polynomial like this, that's what this is called because it's a quadratic, the easiest way to figure out where a quadratic crosses the x-axis is to factor it if it factors nicely. If it doesn't factor nicely, then you use the quadratic formula. So we have to think, how can this factor? We want something that's like x plus something times x plus something, and you spend normally a lot of time on this in pre-calc. So right now we won't go over the details, but if you think about what can I put here and here that will multiply to give me 2 and add to give me 3, you get 1 and 2. If you don't remember how to do this, you could always use the quadratic formula and you'll figure out where it crosses the x-axis. But here, this tells us where, because x plus 1 times x plus 2 must be 0. The only way the product of two things could be 0 is if one of them is actually 0 itself. So that means x equals -1 or x equals -2. So our graph looks something like, let's do -1, -2. It crosses 0 at those 2 points, and we know it opens up. So it looks kind of like this. To figure out where this middle is, it has to reach the bottom at right in the middle, 1.5. So you could plug in -1.5. So you could plug in -3/2 to this and see what you get. But like we realized, that's actually not necessary for this problem because this general shape is enough to tell us that it fails the horizontal line test. Now the way that you can make this problem a little trickier is what if we said f of x equals x squared plus 3x plus 2 for, let's say, x greater than 0. Now we're doing that thing where we explicitly define the domain. And what do I look like when it's greater than 0? Well, we didn't even show that here, but it's going to be something like this. It's just going to be one side. So this one would be invertible, but we wouldn't necessarily know that until we figured out where these actual points were. Similarly, I could have said the same function for, let's say, x greater than -2. Well, -2 is here. So the function for x greater than -2 looks like this. And that is not invertible because we fail the horizontal line test down there. So in this case, knowing the general shape was enough. But if we had restricted the domain, you would need to know a little bit more. This would be the kind of question that might appear on a mini exam. I'm not saying this one's going to be there or anything, but we've got the book problems, especially these simple ones that are very straightforward. And then as you work through Wiley Plus and as you try some of the other problems in the book, you realize how you can kind of generalize the problem that requires you to think about a couple different things at once. This combines multiple ideas. The idea of invertibility, but also the idea of restricting the domain from 1.1. So I'm not saying the mini exam questions are all going to be very hard, brand new things, but they won't be straight out of the textbook. They are supposed to be a little bit more difficult than that. And so if you understand these ideas very well, then seeing them combined like this won't cause you any trouble at all because you'll know what all the ideas mean. And that's what all the practice is for. Okay, last up. This is question number 59. There's a series of questions that say decide if it's invertible, but unlike the last one where it actually is a real function, this is a function that is kind of defined in words, so it's making you think about a concept. This assumes we have a function f of t that tells us the number of customers in Saks Fifth Avenue at t minutes past noon on a certain day. So this function is some kind of box where you put in a time, and you have your function, and it tells you the number of customers that were there at that time. And so you have to think, is this a process that could be invertible? Well, one way to think about that is if we don't know what the graph is, of course, but let's imagine that we had some graph. We only need to worry about positive times and positive numbers of customers. And the question we want to answer is, should this pass or fail the horizontal line test? Now, it's possible that it could pass the test. We don't know, right? We don't know what the actual numbers are. So really the question is asking, is this guaranteed to be invertible or could it fail? So horizontal line test would ask, is it possible for the function to pass through a horizontal line twice? And the answer is, for this function, of course it's possible. Maybe you start out at noon with 10 customers, and then you go throughout your day and you have more customers, and then it levels off and maybe increases more and then falls, and then eventually by the time you close, you have 0 customers. So this passes through this horizontal line twice. So it fails the horizontal line test. And so it's not invertible. Now, it's possible to imagine maybe at noon you start with 1,000 customers and then they leave one by one. That's just going to be a straight decreasing line. That one will be invertible, but it's not guaranteed to be. So really the question is asking, is this function guaranteed to be invertible? And the answer is no. Okay, so those are the 5 exercises. They were pretty straightforward, I think. Remember that there are, on the website, suggested problems in the textbook that you should complete in addition to the graded one. The suggested ones from the textbook are not graded, and they're not collected, but you need to assume that they're part of the required work, even if they're not graded. If you don't do any of the suggested questions, then I think it's very, very likely you won't have enough practice to do well in the mini exams. So you should think about them as being kind of required practice in order to do well. Okay, I hope that helped.